we are recording the session, so yes, be informed that this is recorded. So from day one, Terdo is providing support to application builders in earth sciences. So people working with EO data and algorithms to develop value-adding applications. We are providing a cloud platform as a service and application programming interfaces for the transfer and production of scalable software applications. And our business model is platform-centered. We put together on the platform different actors, specialists in EO data, in processors, specialists on thematics and applications, so that they can interact and co-create together. So for GEP, we have a large community now. We have two main stakeholders, the European Space Agency and the Asian Development Bank, who are managing sponsoring programs for users. And we have on the subscription business model also the capacity to receive direct payments to Terdo for accessing the platform. We are building a governance board that is including the GEP service providers. And the platform is based on virtualization and federation. So we both use this capacity to access cloud compute power and to access remote data repositories for the main EO data missions from Copernicus, from CEOS and GEO, especially the geohazard supersites and natural laboratories, and also to be noted in Europe, the European Plate Observing System, EPOS. And we have two types of EO data processing on the platform. On demand, so that you, as a user, will interact with the service and define parameters and submit a processing job. And we program some systematic processing that will run continuously. This is a quick overview of the statistics. So on average, 200,000 processing CPU hours per year. On average, 5,000 data processing jobs submitted by the users per year. Over time, since 2015, we have worked with more than 300 active users. By active, we mean people conducting projects on the platform with advanced access to the platform, so that using data processing services, publishing results, and providing feedback to improve the platform. On top of this, we have more than 2,700 registered users who have visitor accounts able to search for EO data acquisitions, for shared results on the processing jobs, and public information layers. So we have an offer currently for people who want to access processing services, which is structured in three main pillars. One, basic level access for data screening activities. So it's mainly about visualizing spectral bands and combining these spectral bands for visually identify features. Then essentials, the essentials pillar or pack, service pack, is for event response. So mainly diachronic processing services that will deliver a change detection service with before event and after event image. And then an advanced pack for area monitoring specialists, where we deliver services processing a long time series of EO data sources. We have also a capacity to provide via the Flex program an access to all of these services on demand, and as you want to select any of these from sponsoring institutions. And I will quickly introduce how you can read more about this sponsoring program from ESA, the European Space Agency. So that's the network of resources, NOR, ESA NOR, which is currently our privileged channel for providing science support to users. And so you can find information on the homepage of the GEP, so geohazards-tep.eu. There is a blog post about it where you can read about the conditions. So basically, you will apply for sponsoring, you will present your ID for an application, it will be reviewed and finally approved, and you can get up to processing credits for a budget of up to 5,000 €5,000. So today, the webinar is about wide area subsidence monitoring from space. We are going to have 15 minutes of an introduction on the INSAR background for online services, presented by the members of the GEP scientific animation team. So the scientific animation team is composed of researchers and engineers of the French National Center for Scientific Research. That's the School and Observatory for Earth Sciences at CNRS-UST in Strasbourg, France, and members of the Aristotle University of Thessaloniki School of Geology in Greece. So part of the team today, we have Dr. Floriane Provost. She is a postdoctoral researcher at University of Strasbourg with interest in remote sensing applications for natural hazards monitoring, in particular landslides. And we have Dr. Michael Fumilis, a senior researcher and assistant professor in remote sensing at the Aristotle University of Thessaloniki in Greece. We also have Jean-Philippe Mallet, research director at UST University of Strasbourg. And after that, we will have the presentation of a use case, a science use case by Dr. Francesca Signa. Francesca is an environmental engineer with PhD in earth sciences. She is a senior researcher at the National Research Council of Italy at the Institute of Atmospheric Science and Climate. She has an extensive experience in Earth observation, SAR data, and advanced INSAR techniques for mapping and for monitoring of natural and anthropogenic hazards and risk in urban and rural environments. She participated from the start to GEP at the time in 2015 when we had the early adopters program running. And she has more recently led an activity ISANOR funded, so sponsored by the Network of Resources program, which was focused on monitoring land subsidence and its induced risk using advanced INSAR methods. That's it for this introduction. And so I think now Floriane would open the discussion on the overview of the INSAR techniques.
Yep. I will just try to... hi everyone. So I will basically present very briefly the basics of INSAR and what are the principles behind these techniques. And then I will present the different GEP services that are available for radar interferometry. So to start with, what's exactly SAR? So it stands for synthetic aperture radar, and radar are active sensors that emit an electromagnetic signal toward the ground and receive back the signal. So because of their wavelengths and the fact that they send a signal, they are insensitive to clouds and operative day and night. So they are quite very interesting for those two characteristics. And as they are electromagnetic wave signals are sending, they will be measuring first an amplitude, that is here A1, so it's here the image you see in black and white, and also a phase. So the phase being proportional to the distance between the ground and the satellite plus other components. So what we call exactly synthetic aperture radar is the fact that we will simulate a longer antenna using the motion of the satellite, because we cannot send in the space like very long antenna. We will need to simulate a longer antenna in order to reduce the azimuth spatial resolution. And so the acquisition of the SAR images have a particular geometry, and they are depending on the azimuth direction, which is basically the flight direction, and also the slant range direction. That is also almost the same thing as the line of sight of the satellite, which is called loss. And source geometry makes the fact that the measure is made along the azimuth and the range direction. And so, for example, here is the Mount Etna, and you can see that the topography is a bit distorted, and also the measure of the ground displacement will be done along the line of sight. Now, like if we are interested in SAR interferometry, which is called INSAR, we will try to measure the ground deformation using different paths of the same satellite. So here, imagine we have two acquisitions at different time, and during these two acquisitions, the ground has moved downward, like in the scheme on the left. And so here you will have a first acquisition that will be measuring the amplitude and the phase will be proportional to the distance of the satellite at time 1. And then in the second acquisition, the phase will be proportional to the distance between the satellite and the ground, having moved with respect to time 1. Which is R2. And as you see on the phase itself, you will not see anything different. So in order to measure the ground motion, you will have to compute the difference between phase 2 and phase 1, which is here what we do and what we call INSAR. And you will obtain this kind of very colorful images that contains information, even though it's a weird kind of information, and we call that interferogram. And basically, with this interferogram, you can measure centimetric to millimetric displacement from satellites that are like 800 kilometers in space. So what are those interferograms exactly? So here you can see two interferograms over Mount Etna in 2018 when they were in eruption. And you can see here that there is a first interferogram that is taken in the ascending orbit. So the satellite is going from the south to the north. And then here on the bottom, it's from the descending orbit. So the satellite is going from north to the south. And you can see those kind of butterfly pattern that are like repetition of cycles that you see like blue, red to blue cycle of colors, and we call that fringe. And each fringe is like correspond to a displacement of half of the wavelength of the satellite. So it's what you can see here on the right. It will be like between point A and point B. You will have several succession of fringes, and each time you will have lambda over 2 displacement. So it's not that easy to interpret like that the whole image when you see it as a wrapped interferogram. So there is another procedure that is called unwrapping procedure, and it will do this kind of process automatically over the whole region. So here from A to B, you see that it has added up all the different cycles, and it has retrieved the true displacement of the ground along the line of sight of the satellites, which is really important because you can see here that you have like blue pattern, and then if you look at the other orbit, you have red pattern. So what exactly is going on the ground? And this thing is that as you are looking at the ground deformation along the line of sight, you will have, for the same displacement here in green, you will have a different measure if you look at it in the ascending or in the descending track. And so it's not always easy to interpret the unwrapped interferogram, and you can use both of the orbit to then invert for the east-west and the vertical motion that are more interpretable. So that's basically what you get when you use two SAR acquisition to make one interferogram. Then if you want to go further, you can repeat this step over like several SAR acquisition, more than 20 to 100 of them, and you will try to retrieve the displacement time series over several years, for example. And one of the first important thing to perform INSAR is that the satellite should be in almost the same position in all the acquisitions. So you will look at acquisitions that have very small perpendicular baseline, which means very small distance in space between each acquisition. And if you take here different acquisition, you can compute pairs of, you can compute interferogram in different way. Either you take a temporal reference here and you compute from this temporal difference all the interferogram that have very small baseline with respect to this single acquisition. Or if you want to increase the number of measure of the deformation in between the different acquisition, you can also connect the different acquisition between themselves in a different way, which is a network on the right, and it's what we call the small baseline subset analysis, where you will have a number of interferograms that will increase your problem, and then will resolve for the displacement time series in a better way. So that's the SBAS approach. You can read more in the literature about it. And then the second important thing to perform inside is that the ground will have a good coherence, which means that the structure of the ground and his electromagnetic properties will remain more or less stable in time. And then you will see here that you have a different categories of pixel, or at least scatters on the ground. The first one are noise, so you will have basically no information if you try to compute, if you try to perform INSAR. But then you will have what we call permanent scatters that are very single point scatters or very dominant scatters like buildings, and they will have very stable phase with a high amplitude, and so are very good candidate to perform multitemporal INSAR. And then a second type of scatterers will be what we call the distributed scatterers, and for them the phase is less stable, but they are still above the noise, and they will be also interested target to perform INSAR. So all of that are different approaches that allow to perform multitemporal analysis of the displacement of the ground. And so to finish with what is in SAR, we can look at what are the SAR satellites that are available in the past and currently and in the future. And you can see that there are quite a lot of them today available. And for the first one that were launched was ERS 1 and 2 in 1992. And then since then, we have improved the revisit time over the globe, and we have now with Sentinel-1 a very large and regular coverage of the globe with open access data. And we see that as we go toward the future, we have a number of new satellites that are planned in the future with various different wavelengths. So that's quite interesting. So what we need now is we have a lot of data that are covered, for example, with Sentinel-1 over all the globe. So how to perform and exploit those data. So for that, GEP has developed different services or deployed different services online. And the first one and very basic type of service you can use are called the differential INSAR. So it's really computing with two SAR acquisition, the interferogram, and you have 6 different services that does that on GEP. Some of them are can ingest very old data like ERS and NVSat. Most of them ingest Sentinel-1, and some of them ingest Cosmos Sky metadata. So basically the products of those kind of services will be the coherence, where you can see you can map some faults, for example, here in Ridgecrest, or you can have the wrapped and unwrapped interferograms that are quite interesting when you have an eruption, for example, or also when you have an earthquake. Then we have also advanced services, and there are 3 of them. The first one is FastVail, which also can compute ERS and NVSat time series, and 2 of them are PSBAS and snapping that only ingest Sentinel-1. And also services, they will be very interesting because you can put more than from 20 to 100 of SAR acquisition and perform multi-years analysis, and you will retrieve the mean loss velocity over large areas, and also for each of the point of measure, you will have the loss displacement through time. And except for FastVail that does only propose the loss velocity, but PSBAS and SNAP propose the time series. And so PSBAS is basically using this BAS approach as I described before. It's optimized with parallel computing for Sentinel-1 burst processing. and it will provide the time series and also like the loss, the mean velocity over large area. Like here, it's an example over Java, and you can see that you can monitor different urban subsidence on the island, and for each of the points, you will have a measure of the time series. The other service is called Snapping for surface motion mapping, and it's based on Snap and Stumps softwares, and it's a PSI approach. So it will look only on permanent scatters of the ground. And this service is divided in two different steps. The first one is the snapping EFG, and it will be the step that will process all the interferogram stack. So you have to run that first, and then in the second time, you can run the snapping PSI that will really perform the time series analysis and provide you the time series analysis over the different PSI that will be detected on your area of interest. As an example here is like on the snapping PSI, there are like two different services, the first one is medium res and the second one is full res. And here it's an example of the different service over the airport of Thessaloniki. And you can see that the density of point is significantly increased with the snapping full res. And it's the kind of like result you can get. So you can see that there is a kind of a subsidence over the airport, and you can see the evolution of the subsidence through time for all the points in the map. You can also perform that over a very large scale. Here it's over the Nile Delta, and you can see that you also can monitor like urban subsidence very well. And if you also compare the two services, you can see that you basically can retrieve the same kind of patterns, and if you compare them, you can see that we have a nice agreement between PSBAS and snapping. So it's quite so services are quite robust to measure the ground motion. So that's it for my part. That's kind of an overview of the baseline of the INSAR principle, and also the different GEP services that you can access with a different package Hervé has described. Thank you very much.
Thank you very much, Florian. Thank you. So I see we already have a few questions that are more related to getting access and getting familiar with GEP. So I hope all the links provided are answering. I remind you that if you have science questions, please also use the chat, ask your question, and we'll review these questions at the end of the session. So now I will give the floor to Dr. Francesca Signa. Francesca.
Yes,
again.
hi. Hi, thank you very much. Can you hear me all right?
Yes, very well.
Fantastic. So I'll share my screen, and I think I'll then stop the video because my connection is terrible today. So either the screen or my face. I think the screen will be better.
So far, all is good. We can hear you and see you well.
Can you see the slides in full screen?
Yes, indeed.
Okay, fantastic. Can you hear me all right?
All is good, Francesca. You can go on.
Okay, I'm still here. So thanks again for the invitation, and thanks for organizing this webinar. I think it's a great opportunity for some science catch up as well with the community. So my talk today is about detecting land subsidence hotspots in central Mexico using satellite INSAR, and in particular pushing the interpretation of INSAR results to move from pure observations of ground motion to the generation of risk maps. So you may be informed about the role of groundwater in Mexico. So groundwater is a vital resource in Mexico, as it provides around 40% of the total consumed water of the country. And if we look at continental statistics, it comes out that the country is not, let me say, water poor. but there are several spatial and temporal discrepancies in the recharge and consumption rates, meaning, for instance, that highly populated cities are located in most arid regions. So we have a surplus in some areas, as you can see here in blue, while we have a deficit in some other areas, like in the center of the screen. So as of today, the result is that we have more than 200 aquifers in deficit and more than 100 aquifers that are overexploited. And most of them, as you can see, are in central Mexico. If we look at the groundwater management data from the government of Mexico, we can see that many aquifers are losing their non-renewable storage. In simple words, this means that they are losing their capability or capacity to store water. And this happens because the inputs into the aquifer system is way lower than the outputs through pumping groundwater, for instance. So you can see in the map that there can be volume changes that can reach a few hundreds of millions of cubic meters per year. And this is causing a permanent loss of this capacity of the aquifers to store water. So when the aquifer systems compact, this induces a number of issues on the ground surface, and these are well known and mapped across central Mexico and include cracks, fractures in buildings, the road surface, and also surface faults that are clearly visible across main cities of Mexico, and they generate a lot of damage and economic impacts in urban areas. So with this situation in mind, what we did is to study this process, is to carry out I think the largest insert processing effort in central Mexico using 1,700 Sentinel-1 images. And we used the processing approach that was presented before called PSBUS, the parallel SBUS approach. This was developed by IREA CNR, my colleagues at CNR, and it's running on the GEP. So thanks to the PSBUS approach, we identified more than 30 subsidence hotspots across central Mexico. Many of them are well known because they've been studied by other scholars, by myself in the past, and many other groups, but others are yet uninvestigated in detail. So there is a science opportunity here to further explore. So before moving into detail about how to use the data and how we use the data, we wanted to run a quality assessment of these PSBUS outputs. And we carried out, in collaboration with the National Institute of Statistics, Geography and Informatics of Mexico, we carried out a validation exercise by comparing PSBUS results with PSI results and also with geodetic data from GNSS and leveling. And we could demonstrate that even by using a relatively short stack of 2 years only of Sentinel-1 data, we could reach an accuracy of 8-10 millimeters per year in the estimated vertical velocities. And this is a remarkable performance and perfectly in line with other PSI approaches using the same input data. So moving to the first hotspot, I think this is probably one of the most, let me say, iconic subsidence cities worldwide. It's Mexico City, the capital. And here subsidence rates reach even 40 centimeters per year. And are mainly observed at the lacustrine deposit composing the aquitard. The aquitard is basically the confining layer on top of the aquifer from which the water is pumped. And the sediments of the aquitard are compacting following a power function of their thickness. So the thicker the sediments, the faster the subsidence rates, basically. And this is in response to the fast declining groundwater levels in the granular aquifer. But when we compare INSAR observations with mapped damages and cracks across the metropolitan area, it becomes apparent that issues occur mainly, well, not where subsidence rates are faster, but actually where they change abruptly in space. So every time there is a vertical deformation field changing rapidly in space, so every time there is a significant angular distortion, then some fractures and damages have been mapped in the field. So the angular distortion, in simple words, is a parameter quantifying the amount of differential settlement between 2 points. And thanks to its definition and role, this parameter can be used as a proxy for subsidence induced cracking and faulting. And this is basically what we did to combine information from hazard using INSAR derived information with information about the expected loss by combining exposure and vulnerability of the elements at risk. So what we did basically is to consider the urban properties, so houses across the metropolitan area. And to perform a qualitative risk assessment, we built up these metrics, crossing hazard information from the top and property information from the side. And using this approach, we found that over 450,000 properties in the metropolitan area are in zones of high to very high risk. So as you can see here from the figure, this assessment is carried out at the scale of these little polygons. These are called basic geostatistical areas, or AREBs in Mexico, and they basically comprise groups of urban blocks for which census data about properties and population are available openly to the community. So the risk assessment was done for each of these polygons. Moving to the second hotspot, this is another metropolitan area of Mexico, a bit smaller, but still very highly populated, is Morelia, the capital of Michoacán. The city has expanded significantly over the last 50 years, and the population has also doubled, reaching more than 1 million inhabitants already in 2020. So the INSAR results that you can see here in this map show a number of differential deformation areas which are aligned with the main tectonic faults and contrasting sediment thickness in the basin on top of which the city is built. Though there are a number of features, like rounded features like this one, indicating subsidence zone appearing in heavily densely populated areas, especially new neighborhoods. And this is an area I would like to zoom on to tell you a bit more about. So this is the most apparent example of land subsidence developing at a social housing neighborhood that has been built starting in the 90s. As you can see here in the time lapse, a subsidence bowl started to develop in the 90s, but also in 2005, 2007 by using MVSAT data. This is what we can see. And the bowl started to grow and expand towards the south, following more or less the construction sequence of the different lots. So the situation here, the most updated view of this area is provided by the Sentinel results obtained using PISBAS. And And as we can see, the subsidence bowl has reached an extent of 4 square kilometers and is basically centered on top of an area where new groundwater wells have been drilled to address the demand of water from a total of more than 15,000 inhabitants per square kilometer. So it's an amazing, let me say, density of population for such a small area. So the risk analysis here has been pushed down from the level of the geostatistical units, as you can see in the map in the center, down to single urban blocks, because we had improved resolution data on the elements at risk for this specific city. So we could fine-tune the assessment down to the level of single urban blocks. And as you can see in the maps depicting the area that we were looking at before, there is a clear spatial improvement in the geolocation of the buildings at risk. And also there is an overall improvement in the statistics about risk for this neighborhood. So the improvement is twofold, let me say. So we move now to the third hotspot. This is a very interesting area of interest. It's called the Valley of Aguascalientes. It's running across a walled state from north to south. It's 80 kilometers long and is bounded by two main normal faults, the Poniente Oriente fault, and they are bounding an heavily exploited valley where piezometric levels are going down at significant rates. As you can see here, up to 20, 25 meters in only 14 years. So what can we see from INSAR? So INSAR reveals the typical subsidence pattern when you look at vertical rates, but also the presence of significant deformation in the east-west direction. So we see up to nearly 3 centimeters per year of deformation along the east-west direction and pointing towards the center of the valley, which is like a typical evidence of a subsidence deformation process, especially very fast subsidence occurring in such a geographical and geological context. But this means in practice that when we look at the process, we should consider not only the angular distortions, but also the horizontal strain and the potential development of the so-called areas of hogging and sagging that are caused by the presence of the east-west deformation rate. So as you can see in this schematic view, we are basically talking about areas subject to tensile and compressive horizontal strain, so stress. And as a result, the cracks in terms of location and typology will develop in the buildings in different ways, depending on the direction of such strain. So to assess risk, when you have a situation similar to the Aguascalientes Valley, it's probably better to account for this horizontal strain. And every time the strain exceeds a certain threshold, for instance, you can augment the risk level or risk category by 1 unit, as we did in this particular case. This is not a general and absolute rule. It's our approach to the problem. And you can, of course, tailor the methodology in other ways to adjust to the rules and geotechnical regulations of your countries. You can adjust the thresholds, you can adjust also the threshold specifically used for horizontal strain. So it's up to you. It's not a mandatory set of thresholds, those that are shown on screen. So be careful when you export this approach to other areas. It's our specific choice for these case studies. So Even in this valley, by using this approach, what we saw is that the resulting amount of properties at risk is particularly high. And we found, for instance, more than 25,000 properties in R3 and R4 areas, so meaning very high and high risk level. So to conclude my brief talk, I would like to just point a few key observations. Mainly, the first one is that our quasi-continental survey in central Mexico has enabled the identification of a number of subsidence hotspots, but most importantly, the distribution of properties at risk of surface faulting. And this is key information for land managers and site managers to optimize the use of groundwater resources and try to accommodate future water demand, accounting for a growing population or expanding metropolises, and trying not to exacerbate further aquifer storage loss and impacts on the ecosystems. The risk analysis at the geostatistical unit level can be refined at a more suitable scale by using either information at block level, if available, but also may benefit from improvements in terms of the other input information that you put in the risk equation. For instance, by using more information about buildings, their type, height, maintenance status, but also the market value, you can improve the estimation of vulnerability and exposure. Or on the other hand, you can improve hazard information by using very high resolution SAR data or full resolution inter-processing approaches, for instance, snapping, PSI, and any other available approach. Here, I leave you with some details about the scientific papers where the studies that I presented today are discussed in much more detail. So if you are interested, you can access them, or if you cannot access them, you can drop an email and I can send you a copy, because some of them are open access, some are subscription only. If you want, you can also access those by going to the Terra2 GEP blog. So you go to discuss.terra2.com and search for Mexico. And the first results that you found are 2 blogs where I briefly described these applications and provided the links to the papers. So that's all from my side. I thank you very much, and looking forward to questions.
Thank you very much, Francesca. Yeah, we had a few questions. So there is currently one still unanswered. And yes, we are starting now to receive additional ones. So as we have not so much questions so far, we can go through them one by one. So we have a question from Mauricio Gonzalez, supposing that we have 3 images, 3 data products available for DINSAR analysis with different dates, how to consider the differences in the results by using A versus B, A versus C, etc. I don't know, Michael, do you want to address this? The change that you will detect will depend on the differences that occurred in between the 2 dates that you select.
Yes, so the question in fact is if A and C means A, B, and B and C, which in principle it should be like that. But doing that means that you, once you run A and C, you do the INSAR for these 2 pairs, you have a specific error because of the processing of the images and so on. So if you do A and B and C, you should have the same values with a bit different errors, because you do in fact twice INSAR. So in principle, in theory, it should be the same, but in principle, you will have slight deviations.
Thank you, Michael. As the questions, yes, so thank you, Mauricio, for confirming that you are happy with the answer. Next question is from Muhammad Yunus from Indonesia, Jakarta. Jakarta is facing land subsidence due to groundwater withdrawing. Is there any proof strategy to recharge the underground water and land subsidence phenomena? That goes a little beyond Earth observation.
Well, if I may, I don't have a solution to this, but many other countries are trying to resolve the problem with artificial recharge from nearby aquifers, for instance, or by optimizing the use, and let me say, recycling groundwater when possible. Also, they are trying to reduce the number of instances where you have water leakage from the system. So maybe depending on the typology and maintenance status of your network, sometimes you have a significant amount of groundwater that actually is lost through the network because simply there is a hole in the pipes, so a certain amount is simply lost. So there are different approaches, but well, I'm afraid I don't know if there is a one-way solution, but we have other experts, I think, online who can comment on this particular aspect. So if anybody wants to contribute and raise their hand, I think it would be very welcome.
Okay, I don't
Nobody.
see raised hands so far, so we can move on and eventually come back to this. So the next one is from Estelle Chaussard. Thank you, Francesca, for the great talk. You mentioned vertical accuracy for a certain number of images used in the time series. Do you also know the detection threshold for horizontal motion, and how many interferograms would you need to be able to get millimeter scale horizontal motion, assuming coherence?
Okay, well, there will be a lot to say, but time is short. We've been considering also the horizontal deformation rates and clearly the accuracy on the east-west deformation direction also in that paper. So we could assess accuracy for horizontal motion as well. But regarding the second part of the question, so how many interferograms would you need? No, we haven't investigated this aspect yet, but it's surely an interesting point to investigate for future research. Thank you.
Thank you, Francesca. Okay, moving on in the list. Christo Nikolov asked about atmospheric correction, and I think Michael replied on the chat. Yeah, and Christo is happy with the answer. Daisy has a question for you, Francesca. Is there any increased flood risk in the mid-central Mexico region? Is it going to be a risk assessment part of a future research area?
This is a very interesting point. Actually, in our paper on Mexico City, we've also investigated the effect of increased exposure to flooding due to the subsidence process. In that case, it's subsidence magnitude, the main hazard parameter, and subsidence in Mexico is creating the development of several topographic stratigraphic depressions. It's increasing depressions in many areas across the metropolitan area. And as a result, actually, over the last decades, the population has observed an increased flooding risk every time there are, for instance, heavy rainfalls and so on, because these ponds actually are exposing larger and larger urbanized areas to flooding. And actually, in terms of flooding, there's another issue in Mexico City, because the subsidence is so high in magnitude that sometimes the deformation is, let me say, changing the slope of the sewage network, and also any distribution and service network. So sometimes the slope, it's so modified by the subsidence process that the network is not capable to drain correctly dirty water, or also to provide clean water in the right direction. So there are multiple cascading issues to consider, indeed.
Okay, so while you were talking, Francesca, we got a bunch of new questions. So we have 5 minutes left. We try to at least address quickly each of them. So about the power law, still for you, Francesca, the power law relationship between compaction rates and aquifer thickness, are there empirical coefficients from the literature?
I don't know if there are empirical coefficients applicable to everywhere in the world, but because it's a very specific law that you should consider for each aquifer system. We used in particular a power law because an independent study using non-INSAR data observed a very strong match following a power law relationship between the compaction and thickness. So I don't think there is a set of empirical coefficients applicable everywhere, but of course it's something to investigate, and it's also dependent on the specific geology, specific size and shape of the aquifer, and many other parameters. So I think the answer is no, there are no widely applicable coefficients. So they are site specific, I think.
Okay, we had a question about time series. I will pass on it because I think Michael quickly addressed it on the chat. Then the next one is from Eddie Santoso, geophysicist. They are monitoring earthquake ground motion from accelerometer instruments, which outputs in peak ground acceleration. Is there a relationship among displacement from INSAR and ground shaking or structure failure in buildings? Maybe monitoring precursor of earthquake before it happens.
Okay, I might say to that peak ground acceleration and permanent deformation observed by INSAR is not the same thing. It might happen that the areas affected by high peak ground acceleration, they will show larger damages or permanent deformation. So you will see it also with INSAR. And related to if we can predict earthquakes, I would say that that's a very, very complicated topic. We have seen if the phenomena takes place long, evolving in time, like volcanoes, they will take, you see the building up in magma chamber and so on. You can see that in few images, but it is very, very rare cases that we can do with this, I would say,
Thank you, Michael. Okay, we can do only a last one. So I will take from Héctor Mora Paez in Bogota, in Colombia. Experiencing patchy subsidence, and the concern that has arisen is how to discriminate the results on the one hand due to groundwater extraction and on the other hand due to compaction. Any suggestion about this?
Well, I think land subsidence in Bogota is actually a quite renowned process as well. I've been investigating it only with INSAR observation without going into details. But as a general suggestion to address your problem, there are several studies trying to discriminate the different roles that the different factors and drivers can play in the subsidence process. For instance, you can use principal component analysis, you can use independent component analysis, and try also multi-parameter regression and try to identify which driver shows the highest correlation coefficient with the ground motion. So I can give you suggestions on some papers from the community where these approaches have been attempted, and you can maybe get some inspiration for your scientific study. You are muted, Herbert.
Yes, sorry, thank you, Francesca. We have reached the top of the hour, so we cannot go through questions anymore, but we are monitoring and keeping all those questions, so we can come back to you later on offline via email, for example. We'll make sure also to compile all the questions somewhere on the blog post. So I just wanted as a closing words to really thank you, all of you participating with our speakers also. Francesca, thank you so much. Michael and Florian, thank you for contributing. So this was organized with the help of Jean-Philippe Mallet. Jean-Philippe, thank you also very much. And with the sponsoring of ISA, and Jean-Philippe and Philippe Bali is with us today. So thank you, Philippe, as well. Just to close, because I really have only 2 minutes left, I want to show you the GEP portal and provide you with a few comments about next steps. So for the next steps, you will have to go to the GEP portal, so that geohazards-tep.eu. And here on the home page, you will see down, if you scroll a little bit, we have a summary of the most recent posts on the blog that we relay also on Twitter. And so for some of the questions you had today about accessing processing services JEP, this is the blog post you want to read at the top of the list so far. It will stay at the top for a few days more. And then our announcement of the webinar. And if I open this one, you will see that it's a blog post plus a discussion thread. So below this post, people can provide questions and replies. So this is where we are going to post the link for the video of the recording today. So you will find this video online here. And I'm pretty sure we'll also find a way to make it more directly available somewhere else, but at least you are sure to find it from here, from the homepage and going to the announcement of the webinar. Voila. So thank you again, everybody. Have a nice day. And yes, we are preparing a follow-up. So we'll have another webinar in January. So stay tuned. It will be announced on the blog post, on Twitter. And to you all who have already registered, and it will be sometime in January. So have a happy end of year to everyone, and hope to see you soon. Goodbye.